Okay. Uh, Good evening, everyone. Let me see. Yeah. I want to make sure that everyone can hear me online. Okay, great. Yeah, so first of all, I feel a little bit guilty about the schedule of our class timetable. So tomorrow will be the holiday, but I need to keep you guys until late tonight. Okay. And anyway, I would like to thank all of you who attend this lecture tonight. Right. So last time we have basically talked about classification methods. We spent quite a lot of time on the tree-based algorithms. So we talk about how to do the splitting. First, how to process different attributes. And also we talk about different splitting strategy. And we talk about the measure of no impurity. Basically, they are the criteria that we are utilized to determining which way of splitting is better, and our criteria for growing an optimal tree structure. We talk about the Gini index. So for those measures, we talk about three very famous measures: the Gini index, entropy, and classification error. We introduce the hand calculation examples so that I guess everyone can understand the concept well. We talk about the k-nearest neighbor classifiers, which is pretty simple. We talk about its advantages and its limitations. We talk about a number of key issues in implementing k-nearest neighbors. We talk about the way of determining the value of k, the distance measures, and we talk about that it is possible to using the weighted distance, okay? And we also talk about the Bayes classifier, which is a classification down from the probabilistic way. We introduce a Bayes theorem, which serves as the foundation for us to understand the further Bayesian classifier. In the calculation, we're introducing the naive Bayes assumption, which help us to simplify the computation of the likelihood, which we assume that the elements in this likelihood, they are independent, so they can be decomposed to a set of multiplication. We introduce the example for doing the calculation. We also talk about how to deal with the numerical variable or numerical attributes in these Bayes classifier. So two main strategies. One is using a discretization. Another is more complicated, which is we assume that it follows Gaussian, which serves as the probability density for us to estimate, okay, its probability. So we introduce a complete example of doing a naive-based classifier, which given a test data, a test record X as this, how its label is determined based on a set of computations. Okay. So any questions about the previous contents? Everyone can follow. Okay, I think they are pretty straightforward. So I guess you guys handle it quite well. So far, no questions. Looks good. Okay. Then we continue. Next, I would like to introduce the Bayesian belief network. Okay, which is a little bit more complicated, but it's a natural extension from the classifier by incorporating the network structure. Okay. So basically, the Bayesian belief network provides the graphical representation of probabilistic relationship among a set of random variables. Based on such kind of network structure, we can better and graphically visualize the relationship among a number of attributes. So it is consisted of a directed acyclic graph with the node in this graph corresponds to a variable. So a Bayes belief network, it's a graphical network. Here is a simplest case. So this is a network. Yeah, in this network, each node denotes a variable or attributes in our previous slides. Okay. So A is a variable, B is another variable, C is also a variable. And in this network, besides the nodes, we also have arcs, or sometimes we call links. So those links correspond to dependence relationship between a pair of variables. Okay. From A to C, from B to C, and so kind of. So it has an arrow. Okay, from one variable point to another. So one important thing to implementing this Bayes belief network is you need to generate a probability table associating each node to its immediate parent. Okay. So who are the nodes? Who are in this graph? Who is the child and who is the parent? How to determine the relationship? We can go to the next slides. See how the conditional independence is illustrated in this figure and how the conditional dependence is illustrated in this figure as well. So this is a more extended graph network. It involves 4 variables, A, B, C, and D. So you can see that D is pointing to C, which the arc starts from D pointing to C. So D is the parent of C. Okay, so we say D is a parent of C. So that means C is the child of D. And C is pointing to A, and C is also pointing to B. So we can say A is the child of C, B is also a child of C. So C is the parent of A, and meanwhile, C is also the parent of B. Then we can find that A and D and B and D, they are not directly connected because the whole connection passing through C. But then how can we describe a relationship between A and D and B and D? So you can say B is the descendant of D and D is ancestor of A, okay? So a node in a Bayesian network is conditionally independent of all of its non-descendants if its parents are known, okay? So that means if they are in a similar level, okay, so those variables, we usually call them, they are conditionally independent. So in this graph, who are conditionally independent? Who are in the same level? Exactly, A and B, okay? So basically, they are kind of conditionally independent. So based on the conditional independence, we can also apply the naive Bayes assumption into the computation. Remember, what is the naive Bayes assumption? So in this figure, we can see that Y is the parent of X1, also parent of X2, of X3, of X4, as well as of XD. So X1, X2, X3, X4 to XD, they are at the same level. So they are conditionally independent. Okay. Therefore, the likelihood Px1 X2, X3, X4 to XD condition on Y can be equal to what? Can be equal to the multiplication of the probability Xi condition on Y with I equal to 1 to D. Okay, understand? All right, so we will use such kind of assumption in the latter example as well. Okay. Then next. So the first thing we need to do in the Bayesian belief network is that we need to figure out a graphical network based on the different variables we incorporated into our consideration. So once the graphical network is built, that means the conditional dependence and independence is qualitatively determined well. Then we need to base on such kind of graphical network to produce the probability tables. Okay. So what should be incorporated in the probability tables? That's all the probability happen on the nodes and their dependence relationship. So if X does not have any parents, that means there's a node is the parent of other nodes, but it does not have any parents. Like here, the X has a parent Y, but Y does not have any parent. Okay, so if there's also an X like Y here, which does not have any parents, then the table contains prior probability Px. Okay. If X has only one parent Y, it's like this. Okay. So the first case to avoid the confusion. So if there's an X like this, okay, then this X is just presents a prior probability. So we just have Px here and include this Px into the table. Then if in the second line, if X has only one parent Y, then table contains conditional probability Px condition on Y. Okay. Px condition on Y. All right. If X has multiple parents, Y1, Y2 to Yk, Y1, Y2, Yk, we have an X. They all point to X. Then table contains conditional probability Px condition on Y1, Y2 to Yk. Okay. All right. Here we introduce an example of Bayesian belief network. This slide shows the setup of the Bayesian belief network. And this example comes from a medical healthcare. Okay. So there are 5 variables incorporated in this problem. One is called exercise. Another is called diet. Third variable is heart disease. The fourth variable is called chest pain. And the last one is called blood pressure. Exercise is a binary variable. It indicates whether you do exercise or not. So yes or no. And diet means your eating style. Okay, your lifestyle in eating. So your diet is healthy or unhealthy. Okay. And the third variable is called heart disease. Indicates whether the data record means one patient, whether the patient has heart disease. And the last 2 variables probably are the symptoms related to heart disease, whether has chest pain or whether has and what is the category of the blood pressure, high or low. Okay, so they are all categorical variables. Okay, and based on these 5 variables, the doctor or the domain experts can determine their relationships. For example, whether person do an exercise or have a healthy diet, there are potential factors that will affect, okay, whether the person will get heart disease. And if a person has a heart disease, he might further has a chest pain, or he has some irregular pattern of the blood pressure. Okay. Based on such kind of relationship, we can generate tables of probability. First, we look at exercise and diet. Exercise is a kind of parent of heart disease, and it does not have any parent. So it serves as a kind of prior information for determining whether the person has a heart disease or not. Okay, so it just has a prior probability. The exercise. Okay. So this P exercise has 2 categories. Yes, equal to 0.7, and no equal to 0.3. Same story applies to a dial. The dial is also a parent, and it does not have any parent, so it also serves as a prior. Okay. Things comes a little bit to heart disease. Heart disease is a kind of X who has 2 parents. That means P, HD. Okay, condition on E and D. So E represents exercise and D represents dial. So for such kind of conditional probability, there are how many combinations? There are 8 combinations. Okay. So if HD equal to yes, there will be 4 criteria because there are 2 conditions. Healthy, yes, healthy, no, unhealthy, yes, and unhealthy, no. And for HD equal to no, the same thing. 4 categories. Okay. So here we need to have a table like this. Is that clear to you? Okay. And next, let's look at the chest pain and blood pressure. They are basically the same case. They're at the same level. They have the same parent, heart disease. That means chest pain, condition on heart disease. But what is the relationship between chest pain and blood pressure? They're independent. Okay. They don't have any relationship. They're conditionally independent. Okay, they're at the same level. They have no relationship. So for such kind of conditional probability, then we will have a table like this. CP has 2 conditions. HD also has 2 conditions. So you have a 2 by 2 matrix of probability. Okay. So is my illustration of this figure good enough? You guys?
Sorry, how do you calculate the table, the power table?
Which one?
E equal to healthy and E yes.
E equal to healthy and E equal to yes.
Yes.
This table.
This table, yes.
You want to ask how can we get this value 0.25, right?
Yes.
So if you have this PhD conditional D and E, okay? So basically you are doing counting. So how do you do the counting? It's a counting of all cases. Happens divided by only 2 conditions happen. Okay, so you're counting the total number of the data contains D equal to healthy and E equal to yes, and also counting the total number of the data points, including HD equal to yes, D equal to healthy, and E equal to yes. And you divide by these 2, then it could be equal to 0.25. So if you want to
how do you know the PhD? You find that
it is the data contained in your data set. So you're counting the total number of data points that contains HD equal to yes, D equal to healthy, E equal to yes. You count the number. Then you go through the data set again, counting the total number of data points, have D equal to healthy and E equal to yes. Okay, then yeah, so it's basically counting if you have the database. All right, so once we have such kind of tables set up and the graph set up, then next we do an exercise. How can we do the inference by using the Bayesian belief network if we set up all the things in the previous slides? Here, assume we have a new data set, a new data points which does not have a tag. That means we have an observation with E equal to no, D equal to yes, CP equal to yes, and BP equal to high. Then how can we compute the probability that a person has a heart disease condition on these 4? Okay. So there will be 2 conditions, HD equal to yes and HD equal to no. So we need to compute PHT equal to yes, condition on these EDCP BP. As well as we need to consider the heart disease equal to no conditional ED CP BP. And the value of ED CP BP, they are given no, yes, yes, high. Okay, so that means we obtain the information from a person which the person does not do exercise. The diode is healthy, has chest pain, has a high blood pressure. Then we need to diagnose whether the person has a heart disease or not. Okay. And how can we do the classification? We need to compare the value of these two probabilities. So if the first probability is higher than this one, then we will say that it is highly likely that person has a heart disease. But if according to the calculation, we have inverse results, that means the second probability larger than the first one, then according to the label, we will say that the person probably does not have the heart disease. Okay, then such kind of classification or diagnose is further converting to the computation of two probabilities. Then the question is how to compute the probability PHD given ED CP BP. Okay. How can we do that computation? And why in these slides we have such kind of three items? And why we can say this probability can be proportional to this one. Proportional to this one does describe what? This one describes this probability is proportional to the probability HD equal to yes conditional E equal to no D equal to yes. Multiply the probability CP equal to yes conditional HD equal to yes. Multiply BP equal to high and HD equal to yes. Why we can do such kind of things? Anyone has a guess? So remember the previous stories I have shared with you guys. Go back to this graphical network structure. From this graph, we can see that HD only depends on exercise and diode. It just has two parents. So it is naturally independent from the chest pain and blood pressure. Okay, so this chest pain and blood pressure might be due to the heart disease. It's not that heart disease are due to the chest pain and blood pressure. Okay, so these are the results of the heart disease. And then we look at this equation. What can we do? So we can see that PHD ED CP BP. So if these two guys are independent, we can make a decomposition. Right? We can do the following decomposition. because they're independent. So the E and D, they are not independent. Okay, HD is dependent on E and D, but independent from CP and BP. Based on the naive Bayes assumption, we can decompose it into this kind of structure. Then what is PhD CP? According to the Bayes theorem, is equal to P CP HD multiply PhD divided by PCP. And for the BP, the same story. PhD BP is equal to P BP HD PhD PCP. Okay. If we replace this one with this term and the last term with this one, we can see that PhD and PCP, they are equivalent for these two terms. So they are part of kind of fixed things. So we can ignore this HD and PCP and this PhD and PCP. Okay, and the remaining ones becomes proportional to PhD condition on ED multiply PhD condition on CP multiply PhD condition on BP. Okay. So we can say this term is proportional to these three multiplications. Sorry, I made things wrong. PCPH conditional HD. It's this term. Okay, we take out this term and BP conditional HD. We take out this term. And these two terms, because they are the same, we can ignore them. Okay, we just look at this proportion. They make difference. Okay, all right. So they make a difference in the comparison. This is because PhD and PCP for this condition and for this condition, they are equivalent. So the only difference matters is the BP condition on HD and the CP condition on HD. Okay. So that we can have these three terms multiply together. So from the table, we can find out this one is 0.55, this is 1.8, and this one is 0.85. So we can get the multiplication 0.374. Okay. And for this one, it's kind of 0.0009. All right. Then we get the first probability 0.374 is higher than 0.0009. It does not matter. We can change. Okay, because they are independent. Whatever position they are does not matter. Okay. So then, based on such kind of results, we will say this person has a kind of heart disease. Okay. All right. So next, we finished the Bayesian belief network. Yeah, the support vector machine will be another full story. So how about we take a break here? We come back at 7:55. Okay. Then we will continue as a fuller story. Okay. Okay, so next let's introduce the support vector machine. So basically the following slides will tell you how support vector machine works in the classification. But you don't really need to go to the math principle of this SVM. We will not test it because it's kind of quite complicated, so might not be that suitable for some of our classmates. So basically, if you have data points fall into such kind of two-dimensional space, okay, and we use tags to define the category of those data points. For example, the square mean one class of data points and circle mean another data points of that class. And how can we do the classification? We need to find out a rule which you can separate, will separate these two sets of data points, okay? So this rule can be mean a linear hyperplane which also refers to a decision boundary, which will separate the data. So if we have full freedom, we could have quite a number of options. For example, we can have decision boundary B1. We can also have decision boundary B2 to separate their points to two classes. Okay. But we definitely want to find out the one which is more optimal, okay, which is a better decision boundary. And how can we define which one is better? So here, that's the main idea of the support vector machine, which means based on that line decision boundary, we want to find out a hyperplan which maximize the margin, okay, which maximize the margin between two sets of data points. So the margin means the area, okay, the margin means the area. So if we want to, if we check the B1 and B2, so we use the same slope to move this B1 towards the first and towards across the direction and touch the first point here for one class of data points and move it from another side to touch the first data point of another class. Okay. Then we check the span of this kind of margin. And we do the same thing for the B2. So definitely the margin of the produced by the B1 is obviously larger than the margin produced by the B2. In this case, we will consider B1 is better than B2. Okay, the B1 is better than B2. Then the problem comes, how can we quantitatively determine the margin based on the decision boundary? Here we need to introduce some definition. It is a line, and it is a linear line. So we can define the middle of the decision boundary B1 as a kind of linear boundary, and we set it to and we determine that all the data points fall on this line. They're kind of a neutral value. Okay, it's kind of 0. Then we set two, based on this center line, we set two boundaries, which means all the data points beyond this W multiply X, the slope multiply X plus the bias. Okay, any data points beyond this boundary will be larger than or equal to 1. Okay, and also any data points for another class that means lower than this boundary. Okay, they will be less than or equal to -1. We define like this so that we separate data points into two classes. Then we have X. In the data set, we have the X as well as we have the classes. Now the next problem is we need to determine the W and B, the weight and bias, the weight matrix and the bias, so that we can make this equation hold. Okay, we need to find out optimal W and B to make this equation hold. And based on this graph, we can naturally find out if we consider B1 as the decision boundary, the center line. And how can we determine the margin? We move it until it touching these data points, and we move it across this direction until it touches these data points. Okay, then we need to determine the W and B to determine so that this line will touch the data points this way, and that line will touch the data point that way. And these two data points, we consider they are support vectors. Why it is called support vector machine? Because it is a machine. It is a computing machine to find out support vectors, which finally determine the maximum margin for separating data points into two classes. Okay, so that's the math. That's the story behind the math telling you. All right. So based on such kind of equation, we can formulate the margin equal to 2 over the absolute value, the norm of these weights. Okay. Then how can we do the training of SVM? The training of SVM is to determine the weight and the bias. So we need to determine the best WMB. And how can we determine the best WMB? We have know that we need to maximize this margin, this area. But maximize this margin is very difficult to compute. If we change the denominator to numerator and numerator to denominator, then we will convert this maximization problem to a minimization problem. Okay. And this is a constraint optimization problem because the constraints here, and we can also unify these two stepwise functions, these two stepwise constraints. If we multiply yi on this kind of left side, then we can unify it to yi multiply this guy larger than or equal to 1, always larger than or equal to 1, because when yi is -1, these guys should be always negative. Okay, and its multiplication should be always positive. All right, so it can be unified. And this problem will be solved by using the Lagrangian multiplier methods. Okay, and the simple case can be analytically solved. You can get the dual problem. So solving this support vector machine where you need to touch kind of convex optimization knowledge. You need to know what is the duality. Okay, then you get a dual version of this primal problem and solve it with taking derivative of the dual problem. Then you get the optimal solution. So the mathematical proof behind that could be quite complicated. So if you have some math background, you can check by searching the website, learn by yourself. So we don't require you to understand the proof behind it. Okay. So once the WMB determined or optimized with training, your decision boundary will be determined. So in the future, if you get new data in, if you have data set with the same support vectors, the decision boundary will not change. It will remain the same. Then how to classify the data using SVM once WMB are determined. So given a test record Xi, you take it, you fit its value into it. So if this multiplication plus B is larger than or equal to 1, then you say it belongs to class 1. If such kind of multiplication plus B is less than or equal to 1, less than or equal to -1, then it is -1. Okay, its tag is -1. Then you may come across questions that how about the data points in between the boundary? It is possible that you can have the case that the data cannot be linearly separated. So that means whatever way you change the decision boundary, there will always be some ambiguous data points which cannot be easily separated by a decision boundary. So it means that if you always try the linear separation, you cannot find out a perfect feasible hyperplane to separate all data points to two classes. Then what will be our solution? The first solution is that we don't pursue that perfect results. That means we can tolerate some impurity. We will allow some of such kind of ambiguous data points exist. So in this case, we will introduce a slack variable epsilon here. That means we allow some tolerance on these constraints. So we will not force these constraints needs to be always larger than or equal to 1. We give it some buffer. It can be larger than or equal to some, less values. Okay. So in this problem, we do a minimization, but plus a penalty. This penalty is a summation of those slack variable multiply a learning rate C. And you can see that this slackness is applied to n data points. Okay, for some data points, you don't, because it has been naturally separated. So this slack variable will not have value. It will be equal to 0. But some of the data points you cannot perfectly separate. You have to sacrifice. But our goal is to find out the optimality which consider the least sacrifice. That means least of data points enjoy this penalty. Okay, this slack variable. That means we want to minimize the data points misclassified based on our decision boundary. Okay. So this is approach 1, introducing slack variables epsilon here. Okay. And this slack variable is corresponding to individual data points I. For every data points, you can apply 1 epsilon, 1 slack variable. Okay. Another is we will consider nonlinear decision boundary. For some cases, if you consider linear separation, you won't be able to, whatever you try, you won't be able to perfectly separate these data points to two classes. But visually, we can see that there will be a kind of circle which is able to separate data to two data points. And if we need to mathematically write out this kind of circle, this decision boundary, it will be such kind of this. Okay. So this square plus square larger than something is a definition of a circle. Okay, if you know the high school math, you will know it. And how can we change the relationship from X? And how can we naturally find out such kind of nonlinear boundary? Can we have an approach to convert this nonlinear boundary to a linear case? It is possible, and that is the trick of using kernel functions. That's why when you implement the support vector machine algorithm, one important hyperparameters you need to consider is the selection of kernel function in your SVM algorithm. Okay. So for this case, if we consider a kernel like this, it will naturally project the X from its original space to a hyperplane. This hyperplane, this X axis means a value x1 squared minus x1. The Y axis comes from the original x2 to x2 squared minus x2. And magically, after such kind of projection, the decision boundary can be changed from the original nonlinear circle to a linear separation. Okay. Then we can write decision boundary from the original W multiply X plus B to W to the weight multiply the kernel function of X plus B. And this kernel indicates transforming the original value of X to another hyperplane like this. Okay. Then the nonlinear SVM actually converting the optimization problem, but just introducing a kernel function like this. So we don't need to, so this is just introducing like the same set of equations, but just like replacing the X with the kernel of that X. So you don't need to worry about this math. You just need to understand that it is a transformation of X to another hyperplane so that we can find out a linear boundary to separate the transformed data points. Then the questions comes, given a data set, how can we determine which mapping function, which kernel should be used? And how can we compute, how can we do the computation in high dimensional space? Okay. And most computation actually happens at the dot product between the kernel of transforming X to one dimension and the kernel transforming X to another dimension. And how can we handle that curse of dimensionality? Okay. So there are not infinite kernel functions, but basically kernels fitting for SVM have almost been fully discovered in academia. Although there are so many different kernel functions, but there are some widely utilized one. For example, here, the Gaussian kernel, the hypertangent function, okay, and the polynomial. So a lot of times, you don't need to worry. You just randomly choose one of the kernel and train your SVM and see whether it helps. So this is called tuning of hyperparameters. Okay. 这就是为什么我们要调仓啊 means try, okay, tune parameters, right? Okay. So this shows kind of an example of implementing nonlinear SVM. This is an SVM with polynomial degree 2 kernel. Okay. So it generates a nonlinear decision boundary. And actually it means that after projecting the original data points to a polynomial degree 2 space, we can find out a linear separation of the two sets of data points. Okay. So the advantages of using kernel is you don't have to know the mapping function. Okay. And you're computing dot products of this mapping function in the original space to avoid curse of dimensionality. But not all functions can be kernels. Okay, so must make sure that there's a corresponding function in some high dimensional space. And you can also refer to the Mercer's theorem, okay, to check whether the functions can be kernel. But basically, you just need to try some of the kernels are well known. Those well-known ones means they are most likely works, okay? And for some other very rarely seen kernels, they mean that in most of the cases, they won't make a good results, okay? So please don't need to waste your time on them. Then we go to a general classification problem. We further discuss the classifiers and its performance. So when we evaluate the performance of a classifier, we typically look at the classification errors. So there are three types of errors we can obtain. One is called training errors. That means errors of that classifier we obtained based on the training data set. Second is called testing error or test error. That's the errors we deploy our well-trained classifier into the test data set. And third one is called generalization errors. That's the expected error of a model over random selection of records from the same distribution. So the generalization errors are lessly discussed in real implementation because it has a stronger verification. And most of the time, people will say if the test errors are good, people will accept that classifier. So we're using decision tree as an example. It also tells us how to determine the best number of nodes in decision tree. So this is a decision tree training error graph. This graph shows when the number of nodes increase from 0 to 106 and how the error drops. So if you have very few nodes, you get a high training error, close to 0.5. And when the nodes increases, that means the tree becomes more and more specific. You kind of fitting very well into the data and the error decrease almost infinitely into 0. Okay. If we cut the tree to the scale of just 4 nodes, we cut it here, it's 4. Okay. So the 4 nodes looks like 4 splits. That means you generate 4 rules for separating data points. The tree structure will like this, and the decision boundary in a 2-dimensional space will like this. And each boundary representing a node. Okay, so you're using 4 decision boundary to separate data points into different classes. And definitely you can see you have quite a number of misclassifications, so your error is kind of equal to 0.1. But if you consider a tree with 50 nodes, that means you have 50 decision boundary, very complicated here. Okay, you can see that there's no attention put into further dealing with these parts, but basically inside this very limited area. You can see that the decision becomes a little bit biased, too specific in some parts. Okay. Although it further decreases the error, but the cost is you significantly increase the rules from 4 to 50. 4 to 50. So have you gained any advantages? The question is such kind of cost worthy, or which tree is better? So based on the trial and error, we cannot obtain further information to support our decision or to make any further judgments. Then we need to deploy our tree into the testing data. Okay. So if we look at the tree with the first 9 nodes, we can see that at the beginning, the error dropped significantly in both of training and testing, and until the node 9. You can see that node 9, this gap slightly increased a little bit. The problem comes from after node 9, okay, when you further increase the nodes, although the training error is continuously decreased, but its testing performance becomes worse. The testing error becomes increased. This indicates what? Indicates the previous very specific decision rules, separation of this particular area is quite biased. It is very subjective towards this data set, particular data set, but not generalized enough for other cases. Okay. So this is a kind of very arbitrary, subjective further expansion. And this is called overfitting. Overfitting means you well train a data-driven model towards an existing data set, but such kind of fitting of data-driven models will not perform well in new data set. That means it does not have the generalized knowledge. Okay, it is too specific. So this introduced 2 definitions. One is called overfitting. It means the model is too specific or too complicated or too complex. And the more intuitive observation is that its training error is small, but the test error is large. And correspondingly, there's another term called underfitting. And what does underfitting describe? The underfitting describes that the model is not well trained. It is too simple, so that both training and test errors are large. And you guys might raise a question. Hi, Professor, what if I apply the model and spend quite a great of efforts to train the model in whatever complicated structure into the data I have, but I still get the training and test errors, they are both large. Then what will be your conclusion? Your conclusion will be the method you used to build up the data-driven model is ineffective, which means unsuitable. Okay, that is not a suitable algorithm for you to develop the data-driven model. If you try all possible data-driven or machine learning or even deep learning methods in the world and you cannot get a good results, that basically indicates that your input data points and output data points, they don't have necessary relationships. Okay, they are not linked. They don't have any correlations. So you cannot estimate the output based on the currently input information. You probably need to find other attributes which actually affect the value of the output. Okay. Then how can we address the overfitting issue? So one possible root causes of overfitting is the model is too complex, but the data is too limited. So in this case, you can increase the size of training data to reduce the difference between training and testing errors at a given size of model. Okay, so it means you fix the model into you fix the size of a model you train. You keep on fitting more data into it. It could improve the generalizability of that model. Okay. So here you can see that originally you have a decision tree with 50 models, 50 nodes. You have a little bit limited data points, and you can see its decision like this. But if you fit into more data points into it, its decision becomes more generalized. So the training and testing area become both reduced. Okay. So one strategy of addressing the model overfitting is giving more training data points. So there's two reasons for model overfitting. One is the training data points are insufficient. Another is the model complexity is too high. And what if you have very limited data points? That means you cannot collect more data points for helping model training. Then you have to do some operations on the model size or the model construction. And if we use the tree model as an example, you need to perform the model selection, basically determine the structure of the tree based on the training. So the model selection here means determining the structure of a model in a training. But there's also another concept of a more general meaning of that model selection is in the training of the data-driven model, you apply different algorithms for develop different data-driven model. For example, you select whether your data-driven model needs to be developed by the tree algorithm or the SVM algorithm. So these are the two different understanding of the model selection, okay? In these slides, we particularly focus on using one algorithm, but we control the different model structure based on some parameters of that algorithm. So this purpose is to ensure that the model is not overly complex. That means too specific. And one good usage is we need to estimate the generalization error based on using the validation set. One strategy is we further divide the training data into two parts. One is still training, which basically utilized for building up the model by minimizing the error. The second is called validation set. You fine-tune the parameter of that model you have trained to further minimize the error you estimated based on the validation set. And such kind of strategy is quite commonly utilized if you have very large data set. But it has an obvious drawback. That means if you have a very limited data for training already, then you cut it to training and validation means you have less data for training. Okay. And the model selection for decision tree, that means tuning the decision tree structure. There are two strategies. One is called pre-pruning. This pre-pruning means we grow the tree and we don't grow it to a full structure. We stop earlier when the tree goes to some scale we predefined. Okay. So it is basically stop the tree algorithm before the tree fully grows. And the typical stopping condition for node is composed of twofold. First one is the algorithm will stop if all instances belongs to the same class. That means it already becomes pure in the node. The second is the algorithm will stop if all the attribute values are the same. Okay. But you might not have such kind of ideal cases. You might have more restrictive conditions, more specific conditions to early stopping the tree algorithm. You can stop if a number of instances is less than some of your user specified threshold. That means you don't want to wait until that every node just have one same class. Okay, you can tolerate some impurity. So if you can find out a node already can kind of handle data points of 80% in that node is with the same class, then you already can stop. Second is stop if class distribution of instances are independent of the available features. That means no matter you further split based on the features, the class distribution of the data points will not be changed. That means your splitting does not make any further impact from probabilistic perspective. Then further training means nothing. You can stop early. Third is stop if expanding the current node does not improve the impurity measure. That means your Gini or information gain based on the entropy measure cannot be further enhanced. Then you don't need to further expand. Okay, you don't need to further grow the tree structure. And last one is stop if the estimated generalization error falls below certain threshold. That means the further expanding of the tree structure will impair the generalization error, which will induce overfitting. You don't want that to be happened. You stop early. So besides the pre-pruning, there's another strategy is called post-pruning. The post-pruning is more intuitive or it's more straightforward. You first grow the decision tree to its entirety. That means you grow the tree to the full structure. Then you do the subtree replacement. In the subtree replacement, you can cut the nodes of the decision tree in a bottom-up fashion. So you think some of the nodes does not have any advancement, you can cut it, drop it. So you cut the nodes. If you find out that generalization error can improve after cutting that nodes, then you can replace that subtree by a leaf node. Okay. And class label of leaf nodes is determined from majority class of instances in that subtree. Okay, that is the subtree replacement. You're cutting the subtree structure. And if you find that cut can improve the overall generalization error, then you just replace that subtree with a node. And then you need to determine the class label of that node. And this class label basically is determined based on the voting scheme. So for so many instances, there are different class labels. Who is the majority? The majority will be considered as the class label of that node. Besides the subtree replacement, there's also subtree raising. This subtree raising means sometimes we might not believe that algorithm will go into an optimal path. It might be trapped into some local optimal path. then we will consider whether we can replace some of the subtree with some of our frequently used branches. Just by replacing that subtree with some frequent used branch structure. Okay, that could also sometimes help improve tree, but that is not commonly utilized anyway. So we talk about the model the definition of underfitting, overfitting, and talk about the model selection. Then we further discuss the purpose of the model evaluation. The purpose is to estimate the performance of classifier on previously unseen data. So we want to use the test set to estimate the performance of the trend model. So in evaluating whether the model is effective or not, we will always rely on the test data set. So the test error is the top priority. Most of the time, we don't look into the training error. And how can we determine the test set? Sometimes we use kind of reserve K% for training and 100 minus K% for testing. And we can also do random subsampling to build up the repeated holdout. Or in some cases, we have limited training data points. We can use a cross-validation to strengthen our confidence in validating the performance of our algorithm. So this cross-validation sometimes is also usually called K-fold cross-validation. And this fold means the sub-data set. Partition data into K disjoint subsets. This disjoint subsets means folds. Okay, K folds means K disjoint subset. And the K-fold means we train on K-1 partitions, but test on the remaining one. And some extreme case we'll call leave one out. Okay, that means we set K equal to N. Okay. This N means data points. Then leave one out strategy means we use N-1 data points for training and just use one data point for testing. This is called leave one out. This is obviously a very extreme case. This cannot truly strengthen our confidence on the performance of that model. But in some situation that you have very, very limited data points, for example, for training some very complicated model, you just have 1,000 observations. You have to go with that way. Okay, leave one out. And this is a graphical illustration of the threefold cross-validation. And there's K-fold cross-validation. There are also kind of repeated cross-validation because cross-validation, you have random partition, right? So there's some randomness. You can perform cross-validation for a number of times to get an expectation of the estimation of the performance. Another is called stratified cross-validation. It is usually referred to the data points you have imbalanced response. Imbalanced Y, okay? So for every partition of the data points, you will do a sampling to balance the data points of the class in each of the fold. Okay, so that is called stratified cross-validation. Just kind of cross-validation by incorporating some of the sampling strategy. You can also use nested cross-validation approach for model selection and evaluation. So that means in some of the data partitions, you already do well. and for some of the parts of their points you cannot do well. Then you further do training based on those some data points which are more challenging. Okay, so you do kind of nasty structure, which means you first do cross validation based on the full data set, then further do based on a small portion, and do in a small portion. Okay, so this is called nested. All right, we will stop here and take a break, and then we will go to lecture 5. Come back at 9. Okay. All right, so next we will go to the next part, the regression stuff. So first, let's look at the definition of our regression problem. Basically, it means that given a collection of records different from the classification, what we do is we need to judge the value of the output y. So in classification problem, y is categorical. We determine the tag or the class of y here. We need to directly give the value, the number of y. So the task of regression problem is to learn a model which utilizes to predict the value of y based on the attribute set x. So first we start with the very fundamental linear regression to understand the regression problem. So the linear regression form is written as this equation. So the y is equal to fx. F indicates the linear form of the equation. And more detailedly, this f is equal to beta 0 plus the summation of x multiplied beta j, with j equal to 1 to p. So this p indicates the dimension, or more specifically, the number of x in the input, or the number of attributes. Okay. Then it's linear regression based on the data. What are the data? Data is the y and the x. And what we want to do is we want to estimate the beta 0 and the beta j so that we can have this linear form, get the y estimates, where the y estimates is very close to the observed y. Okay. This is a learning goal then. So we want to do the argument minimization. So the argument is the beta. We want to optimize the beta so that the difference between this estimation of y and the observed y has the minimal residual, have the minimal error. Okay, so this is the error, the fx beta is an equation. Forget the y hat, which is an estimation of y. Okay. So linear regression have a very strong drawback, which means if there are two attributes which has strong collinearity, this beta will hash the values out, okay, and cannot identify the significance of that. Clearly identify which one is more significant. To prevent the collinearity problem of the attributes, people introduce an extension of the linear regression, which adding a penalty after this residual. So this one is a kind of fx beta minus y, okay, square summation. This one is equivalent to this guy. So the difference in the ridge regression is a new term, which is called penalty. And this square penalty penalize the coefficient of each x. And this lambda is a constant. So what does that mean? That means that no matter this x, if there's one x with a beta which is a very big negative value and another x with beta which is a very big positive value, their difference will be hedged out. So we have a square to penalize so that we can really consider which parameters they're important. So if unimportant ones, that means the change of x will make little impact to the y. Okay, so the beta can be penalized. You can minimize that beta. But the ridge regression have a problem, which means in this minimization, no matter whatever beta of j, they cannot be directly minimized to 0. So that people design another extension of the linear regression, which is called lasso, which is able to penalize the unnecessary beta to 0, which directly helps you to make a decision of which variable or which attributes they are useful and which variable they are unuseful. Okay, and why lasso can minimize the attributes to 0 and why ridge cannot, we will look into this very famous figure. Okay, so in this figure, this contour parts means the error space, okay, of or the loss space of that regression model. And this one is the response, okay? So if you see that if we move this contour this way, which means we make the beta estimates close to 0. Okay, we move this way or that way. So we can really touch the point that beta has 0 value with no problem. But here, if we can, this is lasso. But if we consider ridge, as it has a square penalty, beta square penalty, and this beta absolute value. Beta square penalty is kind of a circle as well. So if you move this kind of tables, okay, so you cannot have this kind of touching of beta to 0. You will violate anyway. So based on such kind of shape, the reach can just minimize beta to infinitely approaching zero rather than directly reaching zero as a result. Okay. So we finish linear regression, then let's look at some machine learning techniques. We start with a very simple one, the k-nearest neighbor. So we have seen that k-nearest neighbor has been presented in the classification problem, but it is also doable in a regression. So what is the difference between the KNN classification and KNN regression? The KNN classification is a voting scheme because you need to determine the tag of the response Y. The regression, you need to determine a value. And how can you do that? You just take an average of the Y that your neighbors have. Okay. So that's the value of Y, average value of Y of your neighbors. The same thing, you base on the X to compute the number of neighbors, nearest neighbors of that data points. And based on the value of Y of each of the neighbors, and you take an average. So it's kind of making interpolation, okay? And also the tree can also do regression. So the tree regression idea is a kind of extension of the k-nearest neighbors. But what you do is when you do the split, each of the nodes will have an average value of the response area. So regression tree basically do the partition space of the data and find out the optimal split and how the optimal split can be obtained. This is obtained by taking the average of Y of data points in the nodes of tree as the final estimates. Okay. So for example, this regression tree composed of two parts. Can move this stuff. Yeah. The first part is the indication function. The indication function indicates whether this X belongs to this region, okay, or whether this X falls into that criteria. And the second component is the regression value. It's a CM, which is a constant. That means if the X falls into this region, then Y will equal to this constant. And how does this constant obtained? It is an average of all the Y's of that X falls into this region. Okay. So here is the math illustration of a regression tree. So it is a greedy split strategy, and the split criteria follows this. So first you split the data set into two regions, R1 and R2, region 1 and region 2. Region 1 contains two index J and S, which means for any data points Xj less than equal to a threshold S, okay, this region is a set of that data points of that X. And the region 2 is also defined by J and S. That means any data point Xj larger than a threshold S, then region 2 is a set of that data points. Okay. Then how can you do the optimization? You do a minimization. You want to do the split of the trees so that for every X belongs to region 1, its Y value minus the C1 can be minimized. And for the every data points belongs to region 2, its Y value minus C2 is residual can be minimized. Okay. So you further minimize the overall of those minimization. Then you find out the optimal J and optimal S, which is the optimal split. Okay. You first find out the optimal C, which can minimize the residual of the C1 to the YJ. Okay. Then further optimize the split so that you can lead to the better minimization of C1 and C2. So this is the kind of greedy strategy. Okay, so that's a tree regression. Is that clear? It's quite intuitive, right? Very simple. And next, if no problem, then we go to the SVM regression. So SVM regression has a similar idea, but the concept is replaced by using in a classification, we're using a decision boundary and using +1 and -1 to define the decision boundary. Here, we're using an error term to train the SVM regression method regressor so that the estimated Y and the obtained Y, observed Y, its residual will be guaranteed less than or equal to this epsilon. It means we're using some support vectors to find out such kind of regression curve so that we can guarantee that the errors are less than or equal to this threshold. Okay. So all the other things are similar to the classification with version of that SVM, just that concept change. Okay, this is the SVM regression. The next, we will go into the major contents of these slides, of these lecture notes, which is the artificial neural networks. So basically, we were using handwritten examples to illustrate how the artificial neural network is trained. So we starting with a classification example. But most of the time, the neural network is considered as a black box model that it takes three, in this example, we have a data set of 3 inputs and 1 output Y, which is categorical. And the X's are also categorical, okay? So we want to build up a network structure which is taking the 3 inputs, X's, and to determine the Y. To build up a neural network, first we can define 3 nodes. And each of the nodes is a starting point taking the value of X. Then we're building kind of connections to hidden nodes. These connections indicating the weights of combining these 3 values. Okay. So by combining these 3 values, we're adding 1 bias term, which is a kind of constants. So if you can see these 3 linear integration of the input value and minus this bias term, you will see that it is a kind of linear form. It's kind of linear model. The difference is based on this linear model, we will apply an activation function, which is a sine function here. But here, this sine function is just an indicator of the kind of thresholding indicator to determine whether Y should belongs to +1 or -1. This is the simplest network structure, okay? And this activation function happens on the node, which we consider as the output node. So if X larger than or equal to 0, and this X means this part. If X larger than or equal to 0, this sine X returns to 1. If X is less than 0, this sine function returns -1. Okay, so that we can. Then what we want to do is, based on all the X we observe and the y we observe. We want to determine the optimal value of, we want to adjust the value of these 3 weights and these bias. Okay. So an ANN can be considered as a model, as an assembly of interconnected nodes and weighted links. And the output node sums up each of its input according to the weights of its links. And then we compare output node against some threshold T. Okay. This is just 2-layer network, very simple. Usually we will not see such kind of simple neural network. This can be considered as a linear discriminant analysis model, which the inside is a linear form. Okay, and you have a thresholding. It's kind of can be analogous to a kind of logistic regression model. Okay, but here you're using a sine function as a thresholding. Okay, to judge the output of the linear form and determine whether y belongs to +1 or -1. Let's look at an extended version of an artificial neural network with 3 layers. This is a very classical ANN, which we call multi-layer perceptron, MLP. Okay, multi-layer perceptron. The multi-layer perceptron usually have 3 layers: an input layer, one hidden layer, and one output layer. Just 3 layers. Okay. You can have more hidden layers, then that network becomes deeper. Okay. Sometimes we call that fully connected deep neural network. Okay. But when we talk about multi-layer perceptron in the classical machine learning, it is usually refers to a network with 3 layers. Input layer is a layer contains of all input nodes. Each one of the input nodes means one dimension, one attribute of that input. And we have a hidden layer contains a number of hidden nodes, and the number of hidden nodes are usually less than the number of input layer, but sometimes can be larger. Okay. And people prefer to have hidden nodes less than input nodes is because they want to regard this hidden layer as a dimension reduction of the original input dimensions. Okay. Then finally, the hidden layer becomes a new input to get the output y, the output layer y. In the output layer, the number of output nodes means the number of attributes in the output. So if you just do one estimation of one variable, then you just have one node. If you have a model to simultaneously estimate values for 2 attributes, then you need to have 2 nodes in the output layer. So the key point is in the hidden nodes in the hidden layer. So the hidden nodes, any one of the hidden nodes has such kind of structure. For example, the nodes here is kind of outputs and they are the inputs. All the inputs will be integrated as an SI, okay, and fed into this neuron. And this SI in this neuron needs to experience this activation function to generate an OJ. And this OI, and this OI will be output by this neuron. Okay. And this activation function also needs to take a threshold T. So one key point is how can we determine the activation function of the neurons? It's just like kernels in SVM. In ANN, the activation functions plays very important role. Usually there are 4 popular utilized activation functions. One is called linear, another is called sigmoid. Third one is hypertangent. Last one is a sine function. Okay. So to facilitate the computation, usually in one neural network, we consider applying the same activation function to all the neurons. But there's also a special case that we can customize each of the neuron for the particular activation function. Okay. But that will hugely increase the computational cost. Then we need to go into the Canton perceptron. So each perceptron means a single layer network, just contains only input and output nodes. And it has one activation function, which is a sine. Okay, so it is kind of the previous example we have illustrated. And the perceptron, the learning a perceptron is learning the value of those weights and these thresholds, or sometimes we call bias. This bias can be integrated as W0, okay, for D-dimensional inputs. What we do is for each training example X and Y, we compute the whole function, the whole network based on the W, the weights, and the inputs. Okay. Then we update the weights based on the original weights, the learning rate lambda, and a gradient. Such gradient indicates a direction for optimize the value of this W. And this gradient usually is the difference between the observed Y and computed Y. Okay. And multiply the input value X. That means we take a partial scale of the X to facilitate computing of the W. So we repeat such kind of procedure until the stopping condition is met. Means the algorithm converges, means the W cannot be further optimized. It becomes very stable when you feed in more data points. It will not be changed significantly. So this is a kind of example. Lambda is a learning rate. So the intuition based on this formula, how can we do the update? We update weight based on the error. So if Y equal to fxw, that means you have a good estimation, perfect estimation, then error equal to 0. If error equal to 0, then wk, k means the number of iteration. So w at iteration k will be equal to w at iteration k plus 1. That means no change once the iteration ellipse. If Y is larger than its estimation, for example, error equal to 2, then the weight must be increased. It's positive, so that this weight will be increased. Okay. If Y is less than the estimation, which means error is negative, then the weight must be decreased, so that this estimation will be decreased. Okay, so this is the intuition of the update. It's kind of a control problem. If your observation is larger than your estimation, you want to improve the weight so that your estimation can be increased. Okay. But you might ask that why this error sign determines everything, and you still have an x here. Will the value of x make any contribution? For other data set, definitely x will make contribution. But for this case, if you look at the data we consider, x actually a binary, 1 or 0. It's non-negative. Therefore, the sign of this error matters, the whole thing. Okay, if it is negative, then the whole term is negative. It is positive, then the whole term is positive. Okay. So this is an example of the perceptron training. This is the data set. And this is the number of iteration, a iteration. Okay. And this is the epoch. Okay. This is the epoch. Sorry, this is the number of data points fit into the model. Okay. And this is the epoch, the number of iteration k from 0 to 6, how the W's are updated. Okay. All right, I guess you guys are pretty tired. So tomorrow is the holiday. So how about we stop here? I think you guys don't want to listen anymore. Okay. So we stop here, and I will see you guys next week. But next week we will not have a lecture. So next week will be the tutorial. The TA will take over the tutorial to introducing some coding and practitioners of using some software to implementing some machine learning algorithms we have introduced in this class. Okay. So next week the TA will handle the 3 hours. So that one, I hope the tutorial can help you guys to learn some practical techniques so that you can help with your projects. Okay. All right, so we will stop here, and thank you very much for attending even before the holiday, and see you guys next week. Bye-bye.